Okay, so last time we talked about a penny, and we did make a change. Remember, we said that instead of flipping it or spinning it 20 times, we're going to do it 50 times. What would be the null hypothesis, alternative hypothesis? How do you know which hypothesis is valid? But the one thing we didn't cover was, how do you find the p-value? How do you know how rare your result actually is? And so in this lesson, we're going to do everything, including finding that p-value. So the first thing is, what would be the hypotheses? And so from last time, we could say that the null hypothesis, which means everything's okay, situation normal, is that normally you're supposed to get 50% heads and 50% tails. But the alternative hypothesis, and if there's a tricky part, it's right here. You don't actually change the number. All you do is change the inequality. Instead of being equal to 0.5, we're going to say it's greater than 0.5. Okay, so we found our two hypotheses. Now it says each class found a different p-value. That's assuming that we had done simulations in our classroom, of course, because each dot plot was different. Would it be appropriate to use a normal distribution to model the sampling distribution of p hat and justify your answer? So by saying justify, it means that we've got to do some check or test on the numbers. And in this case, the check or the test that we have to do is large counts, because large counts is what justifies using a normal distribution. We would have to verify that there are at least an expectation of 10 successes and 10 failures. So if we take the sample size times the probability of 0.7, now this is p hat. Remember, p hat comes from the sample. It's not the hypothesized value. It's the one we experimentally derived. So that would be 35, which is at least 10. And if we did the failure, which is 1 minus 0.7 or 0.3, we give 15, which is at least 10 as well. So normal distribution means we can use the Z chart or the Z table. Are there any other conditions we should check? Yes, we should check randomness. And it's a random process because we're spinning a penny. 3 says, now that the conditions have been met, find the mean and standard deviation of the sampling distribution of p hat. We're going to go back to the null value. Now the null value is that 0.5. It's what we hypothesized. So we're going to say our mean is 0.5, and the standard deviation is a formula. It says if you take the square root of the chance of success, the chance of failure, divided by the sample size. Okay, again, we're using the hypothesized value, the 0.5. This turns out to be 0.071. So in a normal coin, in a situation normal coin, we would expect that the hump of the normal curve will be centered around 0.5 with a standard deviation of just about 7%. So number 4, use the mean and standard deviation you found to label the normal curve. I'm going to put actual values on it. So the middle is 0.5, and then 1 standard deviation up means I'm adding another standard deviation of 0.071. So the next one is let me zoom in a little bit, 0.571. Then we add another 0.071 to that, we get 0.642. and then we add another onto that, we get 0.713. Now, going on the low side, now we're subtracting standard deviations. We get 0.429, 0.358, and 0.287. So we can now sort of place on a number line, where is this result we got from experimentation? So number 5, how many standard deviations above the mean is a p-hat value of 0.7? And we're going to label that. So that would be data value minus the mean divided by the standard deviation of 0.071, which gives us 2.81. So our result of spinning a coin and getting 35 heads out of 50 spins would be right about here on the number line. Is that rare? In other words, look at the area of getting something that extreme or even more extreme. And that would be a shading to the right. How much of the total area is that? Well, that's what the z-chart will tell us. So number 6, find the probability of a 50% coin coming up 35 out of 50 or more. So see, we're still assuming that the coin is fair, but we're saying, if it's fair, how rare would it be to get this result? Now, if you go to a z-chart, which I have one here, 2.81 right here in the middle, 0.9975. That's area to the left. But we want area to the right because we want things that are more extreme, even. See, 35 out of 50 would prove our point, but anything larger than 35 out of 50 would also prove our point. So we're going to have to subtract this number from 1. So it's 1 minus 0.9975, which is 0.0025. Now that's what we just call our p-value. Not a proportion of heads or tails, but that means the probability of getting a result this extreme or more extreme. So that was the missing piece we didn't do in the last lesson. We didn't look it up in the z-chart to determine what the probability value is. So now that we've done that, what conclusion can we make? Is that rare? Is it less than 5%? Yes, it is less than 5%, way less than 5%. So we say, since our result of 0.0025 is less than 0.05, we reject the null. So remember, if the p is low, reject the null. So what else? We can say, and we have convincing evidence for the alternative. And what's the alternative? It's basically, in plain English, that the coin is not fair. We got a result that was so extreme, so out of the ordinary, that it makes us question the accepted truth that the coin was fair, and we jump over and we say the coin is not fair. Conditions. We always need to have our conditions laid out and checked. So for the first thing, all year long, we have to have a random process. If we don't have a random process, then everything we collect is meaningless. Okay, but the second thing is we have to make sure that it's normal, that it follows a normal curve. And there's 2 different sets of conditions depending on if you have a proportion or a mean. So let's break those down into the 2 parts. If you have a proportion, then you're going to use large counts. 10 successes, 10 failures. If you have a mean, or if you're using means, there are 3 different ways that you could check this condition. Number 1, it just could already be stated to be normal, already normal. And you will know because when you read the problem, it will say these data are normal. Number 2, kind of run out of room here, is the central limit theorem. Is your sample size at least 30? The sampling distribution of the sample mean becomes normal or approximately normal once the sample size gets to be at least 30. There is a way out of that. If the sample size is less than 30, but you check a dot plot and you see that that dot plot is not necessarily a normal curve like a classic normal curve, but that it is not skewed and it doesn't have outliers, then that is proof enough. So we're just going to say dot plot is good, and that means no skew or outliers. So there's many ways to check if it's mean compared to if it's a proportion. Now the second big idea is this test statistic and then how you come up with the p-value. Okay, so what we had to do is we had to turn it into a z-score. We did the statistic, which means it came from a sample, minus the null value, which is the one we hypothesize about, divided that by the standard deviation. Okay, now in the standard deviation, we have to use the null value for calculating that. We had to use, in this case, p sub 0, which means the null value, 1 minus p sub 0 over n. So if you're thinking that the coin comes up 70% of the times heads, when you calculate the standard deviation, you can't use 70%. You have to go back and use 50% because, remember, we're assuming that the null value is true unless we get evidence otherwise. So we can't use that other value because that assumes the null value is false already. And we don't have any evidence of that yet. And then the last thing is use a z-chart or a z-table to find the p-value. You're in a good spot if you understand the logic and the mechanics of how to do a significance test.